All right, let's do a walkthrough of your survival analysis assignment. So this is a group of all persons under age 18 who were issued a original California driver's license in 2017. It's the same one that was in the lecture, actually. And the question here that I get asked and got asked by the legislature when I worked there is, would raising the minimum age at which teens can be licensed from 16-year-olds 16 to age 17 be expected to reduce teen crash rates? So if right now they can get licensed at 16, if they up it to 17, do we expect that to result in lower crash rates? So that is the assignment. Note that not everything in here we're going to use. First thing we want to do, though, is run a crude Cox proportional hazards analysis. That is the survival analysis. So we go to survival, go to Cox Regression. When we get in this window, select your time variable. Here it's days to crash. We want to move it to the time box. That's how long they were followed up from till they crashed, till we lost track of them or till the study ended. And then we want to take our status variable, which is called crashed, and move it to the status box. And then we have to tell it what level of crash do we want to predict here. Well, we want people who crash. So that's coded up here. If you look, crash, crash, crashed. 0 is no crash, 1 is crash. So we want to predict crashing, right? So a single value of 1, continue, doing good so far. So now we're on 5. Select your independent variable, age license. Note that age license isn't continuous. It's 16 or 17. It's number 16 if they're licensed at age 16. It's number 17 if they're licensed at age 17. And so we want to take that and move it to the covariates box. So that is a categorical variable. So we're going to click categorical, take age license, and scooch it over. So the default here is last. So given that it's 16 and 17, the last or highest value would be 17. So this is, if we leave it as it is, it will tell us the ratio, rate ratio of 16-year-olds versus 17-year-olds, which is what we want to know. We want to know, do 16-year-olds crash more, so that raising the license age would be a good move. So we want to leave 17-year-olds as the reference, so keep it as last, continue. So we do want to get a survival plot. So we go to plots, we click survival, and in case we want to check the proportional hazards assumption, we're also going to get this log minus log plot. That's what we use to check the proportional hazards assumption. Down here where it says separate lines for, we want a separate line for 16-year-olds and 17-year-olds in the plots. So we click it and move it over to separate lines for. I think that's it. Continue. And then to get confidence intervals, which we need for APA write-up, you click options, you do the CI for EXP, click the little box, click OK, or continue, and then we are ready. We're going to click OK and run our crude survival analysis, telling us if 16-year-olds crash at a higher rate than 17-year-olds. Takes a little while to run. These are kind of crazy analyses. So question 1 is the log negative log plot is called LML function patterns 1, 2. It's at the bottom of the output. There it is. Nope. There it is. LML functions for patterns 1 and 2. Does it suggest that proportional hazards assumption was met? That is, are these lines roughly parallel over time? They don't crisscross or anything. The answer is yes, right? Grows over time, but that's what things do when they're log. And they never crisscross back and forth. So we would say, was the assumptions met? I would say, yeah, it does look like the proportional hazards assumption is met. So let's put that. Oh, I forgot to put key up here, which I know I'll totally forget to do if I don't do it now. There we go. All right. Just so I can post this for you guys as well. There we go. All right, so under the section called block 1 at method equals enter, where the heck's that? That's block 0, ignore that. Block 1 method equals enter. Find the SPSS output table called Omnibus test of model coefficients. Under the overall score, this part right here, heading in the table, there are chi-square degrees of freedom, chi-square degree of freedom, and sig. Using alpha of 0.05, does the overall model significantly predict variation in crash rates? Yes, sig is less than 0.05. So simple answer here is yes. This is that overall the model significantly predicted crash rates, right? So that is that sentence right here. So we're going to use the general format for chi-square to fill it in because you might need this for your write-up. So I will copy this down here and paste it. Oh, that's too big there. So we got to fill it in. So let's go ahead and do that. Chi-square of degrees of freedom of 1. Oops, comma. And this shouldn't be italicized. I don't know why everything always is with this stuff. Chi-square with 1 degree of freedom, n is equal to what? Where do we get the n? That's up here, 208,355. So here we do, it's just not going to make my life easy. Is it 208,355? Chi-square is equal to, if I get it right, 208,355. Our chi-square is equal to 36.98, right? If we round that. So 36.98. And P is definitely less than 0.05. So P less than 0.05. And that is how you write that chi-square up. That tells you if the model overall predicts variability. So now we're going to complete the information below using the variables in the equation. This is that one right here. The rate ratio is called EXPB. There it is. The walled chi-square is just called walled. Lovely. There it is. Round everything to 2 decimals. Can do. So your beta is right here. It's your B. So it's negative 0.07. Your standard error is right here, 0.01. Our walled chi-square is there. It's 36.96. And our rate ratio, oh, wow, we're going to put a little star on that. Our rate ratio, why? Because sig's less than 0.05. So that means there is a difference between 16-year-olds and 17-year-olds. Crash rates. EXPB is 0.93. There. Excuse me, here. And our confidence intervals are 0.91 and 0.95. So 0.91, upper is 0.95. We are 95% confident that the true rate ratio falls between 0.91 and 0.95. That's what that means. And this is age 16-year-olds. So let's fill in the blank below and interpret that sucker. Percentage difference formula, we got to use the right one. So we have a rate ratio that's less than 1. So for rate ratio less than 1, it's 1 minus the rate ratio times 100. So that is going to be 7, right? 1 minus 0.97. 1 minus 0.93 times 100 is 7. So the crash rates among driver's licenses at age 17, actually, just to make it clear, let me just show you. So the formula for a rate ratio less than 1, like this one, is 1 minus 0.93 is equal to 0.07 times 100 is 7. So we got 7%. What? Lower or higher? And how did you know? Well, we know that it's 7% lower because the rate ratio is significant and it's less than 1. So the correct answer here is lower. So 16-year-olds crash at a lower rate than 17-year-olds, about 7% lower. So do the findings from the Crude survival analysis support raising the minimum license age to reduce crash rates? Why or why not? No. 16-year-olds crash less than 17-year-olds. So if you raise up the age, you'd expect them to crash more because you have more people getting licensed at age 17. So the short answer here is no, because 17-year-olds have higher crash rates. So therefore, raising the licensing age so that you have to get licensed at 17 or older means you'll have more crashes. That's what this suggests. All right, scooching right along. So this actually happened to me. So you're going through my life. You present the Crude findings to the Legislative Committee on Transportation in California Legislature. They suggest that the effect you observe may be due to a higher percentage of drivers licensed at age 16 being female. They tend to crash less often than males. And again, drivers licensed at age 16 have completed driver's education, which make them better drivers, and more drivers at age 16 could be native Californians, which they think makes them superior as well. So to determine whether differences in sex, driver education, and being a California native could be confounders of your Crude analysis, you decide to conduct one more Cox proportional hazard survival analysis in which you adjust, just like ANCOVA, for these potential confounders and see if there's still a difference between the crash rates of 16-year-olds and 17-year-olds. But first, you need to test whether their speculation is even feasible by seeing whether the distributions for these three potential confounders actually differ between drivers 16 and 17. So remember, in order for those to even be confounders, they have to differ between 16 and 17-year-olds. So what are we going to use to do that? Well, we want to show 16 and 17-year-olds differ in their distributions of sex, driver's education, and being a native Californian, all three of which are nominal variables. Age licensure here is a nominal variable, right? You're 16 or 17. And so we need to do some chi-squares. So we're going to do that. First, we're going to do it for drivers, right? And then we're going to weight it so that we're looking at person time. And person time is the correct way to do it for survival analysis, but the table has both if you look at the write-up. So looking at the write-up, note in table 1, you've got 4 persons licensed at age 16. You've got the percent of drivers who are male and female. You've got percent took driver's education, yes and no, and the percent who are native Californian, yes and no, for 16-year-olds and 17-year-olds. Drivers, person years, drivers, person years. We've got to fill all this crap in. So let's go ahead and do the first analysis as a function of just numbers of drivers. So in the Analyze menu, select Descriptives in Crosstab. In the Crosstabs window, select the IV, which is age licensed, and move it to the columns box. Then select the 3 covariates, that is sex, took driver's ed, and native Californian. And we're going to move that to the rows box. We're going to click the cells button, and under percentages, we're going to click column. So why do we do column? Well, remember the numbers of driver's license at age 16 and 17 were very different. So you can't compare the count of sex between 16 and 17-year-olds because there's more 17-year-olds. There's probably going to be, more of both groups. So the correct way to do it is percent within the independent variable, so percent within column. That's why we're doing column percent. All right. Click continue, click OK, continue. Okay, that's going to run 1, 2, 3 different chi-squares. All right, so what do we get? We get that, I didn't click chi-square, did I? That's fine. So we got among sex, for males, 50.3% of the 16-year-olds were male versus 52.5% of the age 17-year-olds were male. For driver's ed, it was 98.1% had taken driver's ed for 16-year-olds versus 96.6% for 17-year-olds. Native Californian, again, 96.6% versus 94.9%. A higher percentage of the 16-year-olds were native Californians. So I got this little note here. Note that these counts and percents of drivers OD match those shown in the drivers column of the APA write-up. So you do not need to change the values. So what am I saying here? This analysis here was on the same data set. And it turns out the column here for drivers, if you look, was 50.3, 50.3, 49.7, 49.7, 52.5, 52.5, And it matches for all of the drivers columns here. So that's all of these, oops, and all of these. And that didn't quite work, but I hope you get the idea. There you go. You don't need to change these. They already are updated to the correct value. We are going to have to change the person years columns. Okay. I had you run it because you might need to do it, say, for an assessment that's coming up. But for this assignment, that's how you run it by drivers, because you got to fill in table 1, but you don't need to actually change anything to make this assignment a little easier. What you do need to do now is this is counts of drivers, so it always adds the 208,355. That's how many drivers there were, 16 and 17-year-olds. Now we need to actually run this as a function of person years. So we're going to trick SPSS to weight each person by their person time. So out here in our data file, there's a variable called days to crash. This person's going to count as 1. This person's going to count as 2, 8. This person will be 66, etc. We're going to weight them as a function of their time at risk. But first, we're going to convert time at risk from days to years. So let's go ahead and do that. First, convert days of follow-up, days of crash, to years of follow-up, person years. So do this, go to transform and compute. And in here, we're going to call it person years. So I'm going to be super lazy and paste the title in. Stupid SPSS. There we go. Person years. We want person years in the numeric expression box. Here it's called, in the target variable box. In numeric expression box, we want to put days to crash divided by 365.25. So you could literally copy this in right there, or you could say days to crash divided by 365.25. That'll get it for you as well. So when we click OK, check it out. Here's what it did. Out here in your file, it made person years. There was days, it's converted it to person years of days, I guess. So I guess let's find one that's like a whole number. This person right here, 364 days they were followed up and then they crashed. That is 1 person year, roughly 364 divided by 365.25 is apparently it rounds to 1. Oh, there's the full number up there. So it's almost 1, it rounds to 1. But what we did is we converted days to years so that our table isn't too crazy. So now to have SPSS compare the N in percent of person years between driver's license at age 16 and 17, we got to go and weight the cases. So we go to data, we go to weight cases. In weight cases, currently do not weight. We click weight cases by, scroll down, find person years, click it into the frequency by box. Hopefully that's what this says. Frequency variable, okay. Frequency, yeah, it is what it's called. Click OK, that's it. Anything we do now is going to be weighted. Each person counts not as just one value, but they count for the number of person years they were followed up, which can be fractions. All right, to get the cross tabulations of person years for each potential confounder by license group, go to Analyze, Descriptive Crosstabs again. So luckily it saved all our stuff in here. But we want to select a couple more options. We want to actually get the chi-square now, for example. In the window, you should already have age license in the columns box. And sex, took driver's ed, and native Californian in the rows box. That is correct. Do not change it. To add the chi-square test of independence, click Statistics and click chi-square. Then click the Continue button. To add the adjusted standardized residuals so we can interpret them, click Cells, click Adjusted Standardized. Under Residuals, and click Continue, and click OK. And that's going to run 3 chi-squares. One of sex by age, one of took driver's ed by age, and one of native Californian by age. Click OK, boom. These add to 347812, right? Which is not 208355. These are ones where we've weighted by person time. So it is person years specifically. These ones will not match what's in your APA write-up example. They are these columns. So like for 16-year-old drivers, you've got a total of 235,247, not 218,572, and you got to fill in these all the way down. Same thing for 17-year-olds. You don't have 101, 325. You have 1112,565, and so you have to change all these going down. All right, let's do this. So use the weighted crosstab results. You just ran to complete the person years and in percent in the table below. You can tell whether you're looking at the person years versus driver's crosstabs results by looking at the column totals. Total for age 16 is 235,247. 17 is 1112,565. Cool. This is it. Though due to rounding, it doesn't always exactly equal that, so that's okay. That's total is 347,812, 347,812. Here it's slightly off. Rounding made it off by 2 cases, but it's still okay. So let's go ahead and do this. For sex, our percent male is right here. It's 50.4% for 16-year-olds. So 50.4%, or excuse me, oh God, sorry, we gotta do the end first. 118,542. I'll put my commas in later. That is 50.4%. So going across the 17-year-olds, they are 589 right here. 58977, which is 52.4%. For female, that's right here. It's for 16-year-olds is 116,705. And that is 49.6%. For 17-year-olds, it's 53588, and that is 47.6%. And I'll go ahead and put my commas in now so that these are a little more readable. There we go. So that is one of these that we had to get in there. For driver's education, and by the way, that chi-square is statistically significant. For driver's education, that is this table right here as a 347,842 again. For yes, 16-year-olds, we got 231,311, 231,311. That is 98.3%. For 17-year-olds, it's 109, 109, and that is 96.9%. For no, did not take driver's ed, we've got 3,936 here, which is 1.7%. And over here for 17-year-olds, it's 3,456, or 3.1%. All right, kicking butt. And then and again, chi-square is significant, so there's a difference. All right, so 16-year-olds and 17-year-olds differ in both their sex distribution and of person time and taking driver's ed. So let me go to native Californian. This one has a 347,812 instead of 347,8 or 810 instead of 812. It's just rounding. It just kind of works out that way. But this is the correct table. So we get 227 native Californians, 874 for 16-year-olds, and that is 96.9% of all their person time. For 17-year-olds, it's 107,409, which is 95.4% of their person time. For no, it's 7,372 for 16-year-olds, which is apparently 3.1%. And for age 17, it's 5,155, which is 4.6%. All right, that is the numbers we need for the table. So based on the chi-square test for each crosstab using the Pearson chi-square row, so let me go to the first one for sex, Pearson chi-square row, there it is. Blah, 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 blah. And the general format, write the results for each chi-square in APA format and describe how the person times differ by age license. All right, so let me copy this in first. APA, get this sucker in here. Whoops. Make it bold, make it yellow. All right, chi-square for sex by age license has 1 degree of freedom. And again, is 3478812. And our chi-square value is 122.27. P is definitely less than 0.05, so they differ. So how do they differ for the sex distribution? Let's see. So 16-year-olds are 50.4% male, 17-year-olds are 52.4% male. So I would say that either fewer 16-year-olds person time were male or fewer 17-year-olds were male, whichever way you want to say that. I'm going to say fewer 16-year-olds were male, something like that. At least person time anyway. Took driver's ed. I'm going to copy and paste this in there to save a little bit of time. So taking driver's ed is took driver's ed by age licensed. There's our chi-square, 1 degree of freedom, still 3478812, and it's 714.41 is our chi-square. 714.41. Is P less than 0.05? You bet it is. So how do they differ? All right. So 98.3% of 16-year-olds took driver's ed. 96.9% of 17-year-olds took driver's ed. These are significantly different. So we know that more 16-year-olds took driver's ed, right? 16-year-old took driver. That works for me. And why? Because it's 98.3 16-year-olds took driver's ed versus only 96.9% of 17-year-olds took driver's ed. All right, how about being a native Californian? I'm going to copy and paste this again. Native Californian by age license. There's our chi-square, super duper sig, 1 degree of freedom. And just leave the N so it matches the other two. Even though it's actually 2 less, just trust me on that. It's 458.42. P is less than 0.05 indeed. So what do we got? 96.9% of 16-year-olds person time was among native Californians versus only 95.4% of age 17. So a higher percentage of 16-year-olds were native Californians. So I'm going to say more 16-year-olds were natives Californians. All right, let's see if I'm going to get this to fit. It's not looking good, is it? All right, looks like it is going to fit. So higher percentage of 16-year-olds were native Californians. And that doesn't fit very well. We're native Cal, native. I'll just call them natives. Let's do that. All right, so we want to make sure we turn off our weighting. So, or actually, let me back up for a second. So what does this mean? Well, it means that sex, taking driver's ed, and being native Californians are potential co-confounders here, okay? They differ between 16-year-olds and 17-year-olds. I can tell you they are related to the outcome variable. So we need to adjust for sex, took driver's ed, and native Californian. And again, go back in and see if 16-year-olds and 17-year-olds differ in their crash rates. So let's do that. But first, turn off the weighting. So go to data, go down to weight cases, and click do not weight cases. If you don't do this, you'll get this error on the next thing you ran. That's how you know you messed it up. So given that they differ between 16-year-olds and 17-year-olds, let's adjust for those things. So we're going to run an adjusted survival analysis. Now we go to Analyze Survival. Oops, Cox Regression. We want to leave days to crash and crash one and age license as they are, so leave all this stuff as it is. But add the 3 covariates: sex, took driver's ed, and native Californian, sex, took driver's ed, native Californian to the block 1 of 1 box. And there she blows. Now those 3 are all categorical variables, so we have to click categorical, pop these over, categorical covariates box. And then we're going to leave the setting of reference category of last for each and click the continue button. So we're just going to leave it like it is and click continue. And then click OK. That's going to run the adjusted analysis. So number 9, the point of 9 is for you to figure out what is being represented by each of the dummy variables for sex, took driver's ed, and native California. So the way you do that is you look at this categorical variables codings table, and age license is going to be the level coded 1 below, which is age 16. So we're going to put that here, age 16. And they are compared to the age coded 0, which is 17. So age 17. For sex, the group coded 1 is male. So we're going to compare males to the group coded 0, which is female. That's what that rate ratio is going to represent. Took driver's ed is going to be yes, those who took driver's ed, to no, those who did not. And native Californian is going to be yes versus no as well. They're coded 1, so it'll be yes natives versus no not natives. Those are the groups that we want to compare, or will be comparing the way we coded it. So it's going to be 16-year-olds, males, took driver's ed, and are native Californians. Those are the what's represented by the rate ratios. So let's find our log negative log plot again. It's down here called LML, function for patterns 1, 2. And the question is, does it suggest proportional hazards assumption was met? Again, these lines do not crisscross or do anything weird, so they're roughly parallel over time. So you would say yes. Oops. Yes, it does appear that they're roughly parallel over time, so therefore the proportional hazards assumption does appear to be met. So under the section called block 1 method equals enter. All right, there we go. Find the output table called Omnibus test and model coefficients. Here's that. Find your chi-square, degrees of freedom, and sig. They're right here for overall score. Using alpha of 0.05, does the model significantly predict variation in crash rates? Sig is less than 0.05, so the answer is yes. Overall, I mean, if with just age in there, it did. You knew it was going to do so with additional things in there as well. Let's fill our chi-square in. So it goes there. There's our chi-square. Let's fill it in. So we've got a chi-square with how many degrees of freedom? It's 4 degrees of freedom. Oops, not doing good. 4 degrees of freedom, and is equal to what? Well, gosh, where do we get that? 208,355 again. That's the sample size here. So 208,355 is what we got to put here. 208,355. That chi-square value is huge. It's 1766.77. So let's fill that in as well. 1766.77, and it's p less than or greater than 0.05. It's definitely less than 0.05. So the model overall does significantly predict variation in crash rates. All right, so complete the information below from the variables in the equation. Again, we need beta, standard error, walled, rate ratio, and the confidence intervals. So let's go ahead and do this. Is there any way to cheat this by like copying these in? Let's give it a shot. Big bucks, no whammies. Oh God, That like super didn't work. Okay. Don't do that, class. So for age license, it's age 16 again is what it represents. We get negative 0.05. Oops, 5. Standard error is 0.01. Wald chi-square is 19.37. It's significant, so it gets a star. Our rate ratio is 0.95. Confidence interval is 0.93. Upper is 0.97. All right, so how about sex? Sex is negative 0.02 because we're rounding. Standard error is 0.01. Wald chi-square is 2.15. Does it get a star? No star for you. Not significant. Sex wasn't a significant predictor. It's kind of weird. Rate ratio is 0.98. Our lower is 0.96. And our upper is 1.01. That's what that rounds to, right? Driver's education is negative 0.19. Standard error is 0.04. Wald chi-square is 22.08. Significant, you bet, it gets a star. Rate ratio is 0.83. And our confidence interval is 0.77 to 0.90 if we round these two. And finally, native Californian is negative 0.71, round that. Standard error is 0.03. And chi-square is huge, 467.96, definitely gets a star, 6 less than 0.05. Rate ratio is at 0.49. Confidence interval is 0.46. Upper is 0.53. All right, I think we got it. So no effective sex, age, license still differs, driver education differs, and native California differs. And note that all these are less than 1, right? So that means all the significant ones anyway are associated with lower crash rates for age 16, taking driver's ed, and being a native Californian. So fill in the following with blank with percentage difference. You got to use your formula. So we're going to use 1 minus the rate ratio because they're all less than 1 times 100. Rounding to a whole number. Did I forget to do that up here? Did I not round this one to do a whole number? I did, 7%, kid. Sweet. All right, we're going to round these to a whole number. So after adjusting for differences in sex, driver education, completion, being native California, the crash rates among driver's license age 16 was what? So 1 minus 1 point. Let me do it on the calculator again. Let me switch to boring calculator, standard. There we go. So 1 minus 0.95 right there equals times 100 is 5%. So 5%. So the 16-year-old's crash rate was 5%. Is it lower or higher? Answer is lower. Why? Because that rate ratio is significant and it is less than 1. Do the findings from the adjusted survival analysis support raise the minimum licensing age to reduce teen crash rates? Again, no. The 16-year-olds crash less. This is real. So why would you raise the licensing age? The idea is they get licensed when they're under the control of their parents. Their parents tend to put more restrictions on them and monitor their kids driving, and they tend to have lower crash rates. So again, no, the findings do not support raising the minimum licensing age. And it's because 16-year-olds have lower crash rates. So even after we adjusted for these other variables, 16-year-olds still got lower crash rates. Where appropriate, fill in the following blanks with percentage difference using the formula again, rounding to a whole number. So using alpha of 0.05 is sex associated with lower crash rates among teen drivers. Sex, let's see, sig is not significant. So it doesn't matter that this isn't exactly one. If sig's not significant, there's no difference. So is it sex associated with crash rates among teen drivers? It is not in this case. Why? Again, because the sig is not less than 0.05. So the crash rate for male drivers is lower, higher, not different than that of females. It is not different after we adjust for all this crud. Why? Sig is not less than 0.05. That means this is basically 1. And notice that the confidence interval here includes 1 in it, meaning it could be 1, or there's 95% chance 1's in there. So using alpha of 0.05 is driver education completion associated with crash rates among teen drivers. That's all we ask. So driver education completion, significant. So yes, it sure is. Yes, driver education completion is significant and predicts crash rates, right? There's SIG. So the crash rates of drivers who completed driver's education, that is the group that was represented by 1, is blank, lower, higher, not different. Well, let's see. So driver education, 1 minus 0.83, 1 minus 0.83 times 100 is 17%. So those who took driver's education have a 17%. And is it lower or higher? It is lower. How do we know that? The rate ratio is less than 1. It's that simple. Then for drivers who did not complete driver's education. Finally, how about native Californians? Was this significant? You bet it was. So yes, being a native Californian is associated with the crash rates. I'm going to really cheat here and copy this among teen drivers. The crash rate of native Californians is blank, lower, higher, not different. So it's 1 minus 0.49. So 1 minus 0.49, 0.51 times 100, 51% lower. So it is 51% lower for native Californians than for non-native Californians, which is just crazy. So crash rate less if you are a local. So find the survival distribution plot in the example APA write-up. Make the SPSS one for the adjusted analysis. It's called survival functions for patterns 1, 2. Look like the APA formatted one. So let's go ahead and, did I save this as key? Looks like I did for once. God, this was a long assignment, wasn't it? So survival analysis, patterns 1, 2. This is it right here. We've got to change this to APA format, so I might as well do that with you. Double click it, bring it up. This is stands for the percent who do not have the outcome of interest. So it is percentage crash free or something like that. We need to start this at 0. So I'm going to click here, double click under scale, change the minimum to 0, click apply. All right. What else? This starts at 0. Days to crash is not words. So we need to change this to days to crash. And I'm actually going to get a little crazy and say first crash. We got to get rid of this title up here. We don't need it. So I highlight it once, click. Let me see if I can get this right. Click it. I think I hit delete, close. Oh, it's gone. We got to get rid of these grid lines. So that's under options and hide grid lines. And then we got to stretch this out. So this is within the body of the chart itself. So you actually click down here in the space once. And once you get this box, you can stretch this all the way over. And that's it. I think we have an APA format plot now. There's your plot. So make sure you copy and you'll be able to paste it into your APA write-up where you need to, which is way down here. Delete, bam, there she goes. All right. Looking good. So there is some bonus questions. So let me do the bonus questions. What was the average follow-up days for 16-year-olds? What was the average follow-up days for 17-year-olds? How are you going to get that? Well, there's a couple ways to get that. So I think the easiest way to get it, and it's follow-up days, is what I asked for, right? Is to use the explore procedure, which you may or may not remember, but it's under analyze, descriptive statistics, and explore. And remember what this did is it gave you stats and plots as a function for some DVs as a function of some IVs, the factors. So we want for age licensed, that is our factor, the days to crash, because I asked for average follow-up days for 16-year-olds. So I'll put that in the dependent list, days to crash by age license. I'm going to just click statistics, so that's all I get. Click OK. And the average days, this is the output, the average or mean days licensed for 16-year-olds was 611.71. And the average days licensed for 17-year-olds was 605.60. All right. That was really just to remind you about the explore procedure. So the other way to get this, if you wanted, was to do a split file, which I don't think you guys have ever done. No, you have done a split file. So we can do a split file by going over to data, split file, analyze all cases, not compare groups, turn that off, go to compare groups, put age license in groups based on, click OK. And then if I just do like anything, basically I can do descriptives if I want. If I put days to crash in the variables box, click OK, I will get for 16-year-olds, the average 611.71. For 17-year-olds, the average 605.60. So that's the other way. Make sure if you do that, you do turn off your split file, going back into split file, clicking analyze all cases. So that was crazy, which is why it's the only thing this week. So hopefully that wasn't too bad. And if you have questions, go ahead and throw them in the chat and I will do my best to answer them.